Okay, so we have been discussing mutually coupled systems, and they really form the basis for what we're going to be looking at in a little bit about transformers. But now we're going to be taking a look at energy in coupled circuits. So if you remember from DC, the energy stored in an inductor is given by this equation. So energy is 1/2 of the product of the inductance times the square of the current. So that's the definition of energy for inductors. For coupled inductors, the total energy stored is going to depend on the individual inductance and also on the mutual inductance. So now you have the added term, right, due to the mutual terms. And so the total energy is now the addition of, for the mutual, for the coupled circuit, with the two coils, right, coil L1 and coil L2, plus the mutual inductance between the two, then the total energy is going to be given by this equation, right? 1/2 due to this half term due to the first inductance, and this other half due to the second inductance, and this other term due to the mutual inductance. And so the positive side selected when the current both enter or leave the dotted terminals, just like we explained with the dotted or the dots convention. With the total energy equation described for mutual inductors, we can now take a look at what could be the upper limit on mutual inductance. Well, the system cannot have negative energy because the system is a passive system. You know, if you remember, if it's positive, if the system is positive, it's going to means that it's absorbing energy. Power delivered is a negative quantity, and power absorbed is a positive quantity. For a passive system, it's always positive or equal to 0. So if we equate the energy, that we know the energy has to be greater than or equal to 0. If we solve for M in this equation, you get this expression for M, the mutual inductance. So the mutual inductance is always less than the square root of the product of the two inductors in the system. So now, based on that, we can define a parameter called K that describes how closely the value of M, the mutual inductance, approaches that upper limit. And this value is called the coupling coefficient. And the coupling coefficient can have a value from 0 to 1. And it really describes how closely the two coils are magnetically coupled. So it's a measure of the magnetic coupling between the two coils, and is determined by the physical configuration of those coils. So a transformer is a magnetic device that takes advantage of that mutual inductance, okay? So just to go back, we have been looking at mutual inductance and individual self-inductances, but we have now sort of bring those two terms together into what is called the this coupling coefficient, which is really the one that's going to be used when we talk about transformers. So a transformer is in general a 4-terminal device. It has two terminals on what is called the primary coil, and 2 terminals on the other side, what is called the secondary coil. The coil that is connected to the voltage source is normally called the primary coil. And the coil or the circuit part that is connected to the load is called the secondary. And these are called linear transformers if the coils are one on a magnetically linear material. So if the material that are used is either air, wood, or something like that, it's called a linear transformer. Linear transformers are also called air core transformers. It's another name associated with it. So air core transformer, linear transformers means the same thing. So an important parameter to know for a transformer is how the input impedance, Zin in this case, is seen from this source. is important to look at the ENEE because it governs how the behavior of the primary circuit takes place. So if you look at the circuit, you know, we have, again, we have a primary. The primary is the side tied to the voltage source. The secondary is the side tied to the load part of the circuit. And if you look at the circuit, right, on the primary side, if we do a quick KVL or mesh current analysis in the phasor domain, you get this expression, right? You get R1 plus j omega L1 times this current. In this case, because of the mutual inductance between the two, you will have the typical equations that we had before, where this current I2 is going to induce a voltage on the primary, okay? And that voltage in this case is j omega m I2, because you now have this mutual inductance term that it's in the term that includes that induced voltage. Okay, and the sign, of course, since I2 is entering the undotted terminal, then that means that on the primary side, the undotted terminal is going to be positive, and the dotted side is going to be negative. So that's opposing the flow of current that we assume here. So that's where you have a negative, right? So that's for the primary side. In the secondary side, same thing. You have the you know, the normal mesh equation, if you will, or KVL for this side, for the I2 current, which goes through R2, it goes through ZL, and it goes through j omega L2, right? So I2 is common to those elements in the circuit. But also remember, I1 is inducing that voltage on the secondary, right? And that voltage is going to be equal to j omega m I1, right? Well, the sign of the voltage, again, will be found by looking at the dot terminal convention. So on the primary side, I1 is entering the current on the dotted side. So that means that on the secondary side, point this out just a minute, on the some room. So when I1 enters the primary on the dotted side, is going to induce a voltage, excuse me, it's going to induce a voltage positive at the prime on the dotted side, negative on the undotted side. So again, this voltage induced by I1 is you know, is the opposite direction of this current, so that's why you have a negative on here. Okay. In other words, if you do a KVL, this will be a negative voltage because we assume we're going in this direction for the positive, right? So that's why you get the two equations here for the primary and for the secondary. So if we express I2 here in terms of I1, the second equation, right? Or rather, you know, if we get I2 in terms of I1 in this equation and substitute back into this one, and then you get this expression for V over I1, which is the input impedance, right? So if we do that, if we divide those two terms, we get an expression for the input impedance that has these components, where this first two terms correspond to the primary impedance, right here. And the second term is what we call the reflected impedance. Okay? And the reflected impedance is due to the coupling between the primary and the secondary winding. So again, we have determined what the input impedance is looking into the primary based on these two equations, and of course on the fact that the impedance is equal to the voltage over the current I1. All right. So for example, we're going to use that that technique, if you will, that method, to calculate the input impedance and the current I1 in this circuit. So if we calculate the impedance, the input impedance, we could use the equation we just generated in the previous slide, right? So if we do that, then the input impedance is going to be equal to Z1, right, which is this term here, plus J20, right? So this is the primary elements in the circuit, plus the reflected impedance, which is this term here. So the reflected impedance, again, is going to be equal to, if you notice from here, it's going to be equal to omega square m square, because if you remember, for the mutual impedance, right, this J5 ohms is really equal to J M5, right? So that's what this representing here. So when you square that, it's just the 5 that you're squaring, right? The omega square m square is just the 5 squared for this term here. And on this bottom side, then you have R2, which is going to be equal to, or the second element, whatever that element is. Remember the previous one, when we derived this equation, right? We have this R2 here and this L2 here, right? That's what this comes from. So for this one, you're going to have whatever Z2 is plus ZL plus this term J40, right? So you're adding all the terms in the numerator here that correspond to the secondary side. Okay? Maybe not in the same order, but you know, that's what you have. So if we do that, since we are given Z2 and we are given ZL in this problem, right? We can substitute for those values, and the rest is just math. So the rest is the math. And so we find the input impedance given by this value. And so then we can find the current based on that input impedance. Okay. So in an ideal transformer, this coupling coefficient is going to be equal to 1. Okay. Remember, we defined the coupling coefficient as this ratio. And it's a measure, again, of the magnetic coupling between two coils. It can be from 0 to 1, but for what we call an ideal transformer, K is always equal to 1, so that means that there's 100% coupling. Okay. An ideal transformer has 2 or more turns with a large number of windings on a core that has high permeability, and it has 3 characteristics. The coils have very large reactances, approaching infinity in the limit. The coupling coefficient is equal to unity, and the primary and secondary coils are lossless. Okay, those are the 3 characteristics of an ideal transformer, what we call an ideal transformer, besides the fact that they have a coupling coefficient of 1, 100% coupling. So what does that mean when we look at ideal transformer? Well, it makes things a little easier to work with, and we'll see why in the next couple of slides. Again, if you look at this circuit, again, we can look at, we don't even remember if the two currents are entering the dotted terminals, then you know that the signs of the induced voltage are going to be positive, right? So we don't have to go through the dot convention again, because we kind of know that already. Excuse me. So okay, so we have the equations for V1 on the primary, right? Again, the self-induced term here, the self-induced voltage, and the mutually induced voltage is due to I2. For V2, you have the self-induced voltage here due to I2, and the mutually induced voltage due to I1. Again, the signs are positive because of the 2 currents entering the dotted terminals, right? So if we solve for I1 in this first equation and substitute into V2 here, you get this expression, okay? But if you remember that M for a perfect coupling of 1, right? Remember, if m is equal to, if k is equal to 1, right, for perfect coupling, then m is just going to be the product of the L1 and L2 square root, right? So if we substitute for m into this equation with this product, we obtain this result, right? And if we multiply, so now if you notice here, right, if you carry out this addition, if you will, of fractions of L1, right, when you multiply L1 by this term, right, then you have, or in other words, if you multiply both sides of the equation by L1, then on this side, you're going to get j omega L1 L2 I2, which will cancel with this term right here, right? So you will get, if you multiply both sides by L1, you get L1 here, and you also get L1 here, right? Over L1, right? Because everything will be under L1, right? So, cross multiplication, right? So this term here is going to cancel, right? So that term is going to cancel, and then if we end up only with this value, right? L1, the square root of L1, L2, V1 over L1. If we multiply that both sides by the square root of L1, then you ended up with this, right? So by multiplying both sides by L1, the square root of L1, the square root of L1, you get this expression. And then we call this ratio of the square root inductance 1 over inductance 2 over inductance 1, we call that N, okay? And we call that the turns ratio. Okay, so we give that name to this expression. It's just the turns ratio for the transformer, for an ideal transformer, okay? So in the case of iron core transformers, they're very close to ideal. So in the future, we're going to use this symbol here with the 2 bars in the middle, parallel bars, to indicate that this is a core transformer, or to indicate that it's an ideal transformer. That will be the notation or the symbol used for an ideal transformer, right? Of course, an ideal transformer physically includes some kind of core where you have the coils turn around one side, and coil or the coils turn around on the other side, right? So for an ideal transformer, this is the symbol that we're going to use. And we call N1 the number of turns in the primary, and N2 the number of turns in the secondary. Okay, because if you remember, the number of turns affects the inductance, right? You remember from the original equation or definition of inductance, inductance is directly related to the number of turns in the coil, right? The more turns you have, the higher the inductance, okay? So if you remember what we define or what we talk about as Faraday's law, right? Defining the voltages related to the coil, the number of turns around the coil in an inductor. The voltage induced by a changing flux with respect to time is equal to that voltage. That voltage is equal to that changing flux times the number of turns. Okay, so that's the definition of a voltage induced when you have a changing flux, which is very depending on the number of turns. That's what defines Faraday's law. So if we divide this voltage V2, which is the voltage across the primary coil, over the voltage V1, which is the voltage across the V2 is the voltage across the secondary coil, I'm sorry, over the voltage V1 across the primary coil, then this term, the of the differentiator term will cancel, and you have N2 over N1, which is equal to the turns ratio, okay? So that's another definition for the turns ratio. Remember, we define turns ratio as, excuse me, L2 over L1, right, from the previous expression. So we also have redefined that term as N2 over N1, where N2 over N1 is the number of turns associated with the two sides of the transformer. Okay, so this is again called the turns ratio or the transformation ratio. So using phasors in this expression will result in this, right? If you divide the two phasor voltages, then is equivalent to dividing the two turns ratio. The turns ratio in the secondary over the turns ratio in the primary. Okay, and so another symbology or terminology that is used when you look at ideal transformers is that the turns ratio is usually indicated like this. So you have 1 to n ratio, okay, where n will be this number, whatever that number is. It's an integer number. Okay, so again, that's the definition based on the ratio of voltages. So by conservation of energy, again, the energy supplied to the primary is equal to the energy absorbed by the secondary, right? Because remember, the primary is the one supplying voltage. The secondary is the one absorbing that voltage with the load in it. So in terms of energy, right, or power also, because power is the, or rather the energy is the, if you differentiate the energy, you get the power, right? So the product of voltage and current, if we multiply that, we get this same expression here, right? In terms of the turns ratio. So for an ideal transformer, the turns ratio is always equal to the division of the secondary voltage over the primary voltage, or the primary current over the secondary current. Okay, so those are the two expressions we have for turns ratio. Okay, and in the case of so you just gotta be careful because this swap, the order swap. But if you keep the same order, so I2 over I1 will be 1 over n, V2 over V1 will be just n. Okay, and this is important because this turns ratio n defines the function of the transformer. If n is equal to 1, we call this an isolation transformer. Why? Because if n is equal to 1, then that means that the voltage in the primary is equal to the voltage in the secondary. There's no change in voltage. It's just an isolation transformer. If n is greater than 1, then the voltage is being increased. So we call this a step-up transformer. If n is less than 1, the voltage is being decreased on the secondary side, so we call this a step-down transformer. Okay? So the ratings for transformers are usually specified as the primary over the secondary. Primary voltage over secondary voltage. So a 2400 or 120 volt transformer has 2400 volts on the primary and 120 volts on the secondary. So this will be a step-down transformer. And normally the ratings are going to be given in RMS values. Okay, when you look at the ratings in a transformer, those will be indicated as RMS values. So again, this example here of a 2400 volts in the primary over 120, which is 120 volts on the secondary, indicates a step-down transformer. If the polarity of the voltage or currents is changed, then n may need to be replaced by minus n, depending on the polarity changes. And so this summarizes what we discussed so far. Okay? The ratio of voltages and the ratio of currents. Okay? Just being careful that you know, this number flips because of the relationship between voltage and current when you talk about the same, with reference to the same secondary. Okay? And again, this is from the same equations on the left. You get these expressions, right? So there are rules for getting the polarity correct for the transformer in the circuit. If V1 and V2 are both positive or both negative at the data terminal, use plus N. Otherwise, use minus N. If I1 and I2 both enter or leave the data terminal, use minus N. Otherwise, use plus N. This is similar to the dot convention, and you'll see that it's got the same type of use. So if repeating this again, if V1 and V2 are both positive or both negative at the dotted terminal, then use positive N. Otherwise, you're going to use negative N. So if you look at this first example, right, V1 for figure A, V1 and V2 are both positive, right, at the dotted terminal. So you're going to use a positive N, right? Little n, which is the ratio of n2 over n1. Remember this here, right? And so this is an example of that. Let's look at another one here. Same thing here, right? For voltage, see how voltage is positive. V1 and V2 are positive on both the negative, I'm sorry, positive at the data terminal on both positive terminals, data terminals. So the ratio n2 and 1 is going to be positive. So in this case, B. So if I1 and I2 are both entering or leaving the data terminal, you're going to use minus N. Otherwise, you're going to use plus N. So in this case, current I1 on figure A, current I1 is entering the data terminal. Current I2 is leaving the data terminal, right? So one is entering, one is leaving. So that's why this is positive. Okay. On this B circuit, I1 is entering the data terminal. I2 is entering the data terminal. So if both are leaving or entering, then the sign is going to be negative, right? That's why you have a negative here also in case D, right? Because this current I1 is entering the data terminal. This I2 is leaving the undotted terminal. So you have a negative sign, right? And the same thing if you notice on the circuit D, if you look at this first statement, right? V1 is positive at the dotted terminal, and V2 is negative at the dotted terminal, right? So that's why you have this minus N here, okay? So those are the rules for ideal transformers with respect to the number of turns, or to the turns ratio. Also, if we remember, of course, the definitions for the turns ratio in terms of voltages and currents, right? If you look at the complex number in the primary winding, right, given our equation that we already know, for the primary winding, the voltage and the product of the voltage and the complex conjugate of the current will give you the complex power, right? If we substitute for I1 and for V1 using these equations here, right? So in other words, V1 is going to be equal to V2. If you look at this equation, V1 is going to be equal to V2 divided by N, right? So if we substitute for V1 in terms of the turns ratio, and if we substitute for I1 in terms of I2 using the turns ratio, you get NI2, right? Which you will get that. So what that's proving is that the complex power in the primary winding is equal to the complex power in the secondary winding. So again, this shows that the two complex power are equal because the complex power being delivered by the source is equal to the secondary power absorbed by the source, assuming there's no losses. Because this is an ideal transformer, right? The ideal transformer absorbs no power. It is an ideal transformer, and there's no losses in it. Okay. And again, if we use the input impedance as looking again our normal circuit for a transformer, right? If we look at the input impedance for this ideal transformer, it'll be equal to the voltage divided by this current I1, right? But if we now, so it will be the voltage divided by 1, but if we now use the expressions for V1 in terms of V2 and for I1 in terms of I2, you get this expression here. And so what that means is that the input impedance, and of course V2 over I2, again looking back at our model, V2 over I2 is our load impedance, right? Right here. So if we look back into this expression, then that means that this V2 over I2 is the load impedance. So that means that the input impedance is equal to the load impedance divided by the square of the turns ratio. And again, this is what is called, this Zn is called the input impedance or the reflected impedance also, okay? The reflected impedance. Again, so the input impedance that shows at the source is equal to the load impedance divided by the square of the turns ratio. And this is important because when one looks at impedance matching, because when you look at matching the impedances, you get again maximum power transfer. So let's look at one example here. In this example, we have an ideal transformer. Is rated 2400, 120 volts. And again, given our convention here, we already know that the primary then has 2400 volts. The secondary has 120 volts. And those are RMS values. And then this ideal transformer is rated also 9.6 kVA, and it has 50 turns on the secondary side. Okay, that's what we know at this point in this ideal transformer. So we want to find, the first thing we want to find out is the turns ratio. And then we want to find the number of turns on the primary side, and finally the current ratings for the primary and the secondary sides. So the turns ratio is actually given by the voltages already, right? These voltages here are already defined in the turns ratio, right? So the turns ratio is equal to the voltage at the secondary divided by the voltage on the primary. The voltage at the secondary is 120. The voltage on the primary is 2400. So the turns ratio is 0.05. So now that I know the turns ratio, right, and I know that the turns ratio is defined as the division of the number of turns on the secondary over the number of turns on the primary, okay? And they give me the number of turns on the secondary side. So if I solve for M1 on this expression, right, because I know the turns ratio, I know the number of turns on the secondary, so the number of turns on the primary is 1000 when I solve for that. Okay, so that's how I found the number of turns on the primary because of this relationship between number of turns on secondary, number of turns on the primary, and the turns ratio. Okay, now they want to know the number of turns on the primaries. Oh, this is what they were looking for, number of turns on the primary side. The first thing we were looking for was the turns ratio, which is already given, like I said, by just dividing the two voltages. So the turns ratio is already here. The number of turns on the primary we found from that expression also. And the last thing we're going to find out is the currents on the primary and secondary. And so, but they're giving us also another piece of information here that's going to be useful for us to find that current, and that is the complex power, right? 9.6 kVA. So since we know that in an ideal transformer, the complex power is the product of the voltages and currents on the primary, or the voltage and currents on the secondary, and in this case, that's going to be equal to 9.6 kVA. So if I solve for I1 on this first expression, since I already know V1, right? V1 is 2400, the primary voltage. and I know the complex power, I can solve for I1. So I1 comes out to be 4 amps. Okay, and so I can do the same thing for I2, right? Since I already know the voltage on the secondary, then I get an expression for the current on the secondary as 80 amps. And I could have done the same thing. I didn't have to go through this other step of finding the current I2 from here, since I could have used also this expression, since I already know the turns ratio. I could have found current I2 and I get the same number. Okay, and at this point, remember, we're only looking for the for that rating for the current, right? Or how much that is. That's all that we're looking for in this case. All right, there's another way of solving this type of problems when you have a transformer. Okay. In other words, when we want to analyze circuits like this, they have transformers, especially when you have an ideal transformer like this. There's another technique we can use. Okay, and we kind of already look at that already when we looked at the reflected impedance concept that we just discussed, if you remember. And the idea is that we could theoretically remove the transformer by doing a transformation. Okay, it's just a transformation. It's nothing physical, obviously. We're just doing analytically to analyze the circuit. We can remove the coils by doing a what is called a reflecting impedance concept, and that's what this section is talking about. We can remove the transformer from the circuit by adding the secondary and primary together using a couple of rules. And these are the rules, and I'm going to read them, but it make more sense once we do some problems. So the general rule for eliminating the transformer and reflecting the secondary circuit to the primary, because what we want to do is, okay, let me go back to the model here. The model for the ideal transformer, right? We're saying, well, we can remove this transformer to make the analysis a little simpler by what is called transforming the primary onto the secondary, right? And you'll see how this makes sense. Or we could transform the secondary onto the primary, okay? And that's what those statements are referring to. So it says, the general rule for eliminating the transformer and reflecting the secondary circuit to the primary is to divide the secondary impedance by the square root of the turns ratio, divide the secondary voltage by the turns ratio, and multiply the secondary current by the turns ratio. Now, at this point, this doesn't mean a lot, but you'll see how simple it is by just applying it. And very similarly, we can do the same thing on the other side. The rule for eliminating the transformer and reflecting the primary circuit onto the secondary side is to multiply the primary impedance by the turns ratio square, multiply the primary voltage by the turns ratio, and divide the primary current by the turns ratio. Okay, well, at this point, this doesn't mean a lot, but this is our guidance for how we're gonna apply this technique. So this explains it a little more graphically. Remember, this is our original transformer, ideal transformer circuit, right? Again, remember, these bars here indicate that this is a iron core transformer or an ideal transformer. This one N indicates the turns ratio for this transformer. We have a primary and we have a secondary, okay? And so the method says that, okay, well, we could, we can analyze this transformer circuit that we have here, and we can analyze it by removing these two coils, and removing these two coils and joining the two circuits together. And that's what we have here, right? We remove the transformer, okay? And removing again in quotes, right? we're removing the transformer by, in this first example, in this case, this circuit on the left, by reflecting the secondary circuit to the primary side. Okay, so we get, in this shows the secondary the secondary circuit being reflected to the primary side. So what we do is, remember, as the previous statement says, we divide the impedance by the square of the terms, right? So this will be this first case here. We divide the secondary impedance by the square of the turns ratio, divide the secondary voltage by N, and multiply the secondary current by N, if there's any in here, right? Okay. On the other side, if we decide to reflect the primary circuit to the secondary side, okay, then we multiply the sources by N, and we multiply the impedance by N squared. And that's all there is to it. Just by doing this, we eliminate this, you know, we're really doing the work that we already did before when we did the analysis, doing, you know, the mutual inductance and all those things. So we just impliedly using it so that we can come up with just a single circuit instead of having the transformer. And if we look at this example, you see how this is really very simple. So in this case, we have an ideal transformer. Again, I know this is ideal because of this terminology here. And we want to find the source current. And we also want to find the output voltage here and the complex power supplied by this source. Okay. So we're going to use the method to transform the impedance so that we can eliminate this and come up with just a simpler circuit, right? So the 20 ohm impedance at the load can be reflected to the primary side. And the way I do this is by dividing that impedance by the square of the turns ratio. So in this case, again, the turns ratio, remember, is 2, because you have one N, so this is 1, 2 in this transformer. So the square root of turns ratio is 4. So this impedance, when I do the reflection, is going to be equal to 5 ohms. Okay, so doing that now, you know, I'm doing this, if you will. Doing that, then I have for my input impedance, I'm going to have 4, which is this term here, minus J6 plus the value of the reflected impedance. Okay, so since the reflected impedance had a value of 5, right? That's all there is to it, because it's just a resistor. There's not much on the secondary side other than this load, right? So on the input impedance side, what I have is this 4 plus, because this model here that you see here is a more it has a source in it, but in our case we don't have a source, right? We don't have a source, and this impedance here is just a resistance. So that's what we have now. When we did this transformation and divide the resistance by 4, right, which is the 20, and we came up with a 5. This thing here was replaced by a 5 ohm resistance. So now what you have is this impedance Z1 for the primary, which is 4 minus J6, plus the reflected impedance, which is 5, and that gives you 4 plus 5 is 9. And that's how you come up with the input impedance. Okay? All right, but remember, this is the more general case when you have a source. In this example, on the secondary side. On this example, we don't have a source on the secondary side, so it's just a resistance. So now that I basically have, again, I just have a circuit. I converted everything into this circuit, and let me do it again since it make it easier to understand. I don't have a source on the on this side, right? You just have a wire, and on this resistance here is replaced by a 5, or this impedance is replaced by a 5, which is a reflected impedance now. So my circuit now, if I want to find I1, right, which is what I want at this point, is just this voltage, which is this 120 volts, divided by the input impedance, which I just found out, which is the combination of these two impedances. And that's what gives me I1, right? That's how I get I1 from here. So in this example, I1 and I2 are leaving the dotted terminals, right? And so then that means that the dotted terminals, that's right. So if you look at this example here, I1 is leaving the dotted terminal, I2 is leaving the dotted terminal. Or you also can say I2 is entering the undotted terminal, and I1 is entering the undotted terminal. Whichever way you want to look at it is the same thing. But the point is that one is leaving and one is entering, right? Whether it's the dotted or the undotted terminal. So therefore, this sign is going to be negative according to our convention, right? Remember that? So I2 is going to be equal to 1 over the turns ratio times the primary current, negative because of this convention that we have, that one is leaving and one is entering, okay? And so now the output voltage is going to be equal to 20 times that current I2, or 110.9 at an angle of 213.69 volts. All right, so now the complex power supply, again, is given by this expression. We already know what the source voltage is. We already know what the primary current is. We take the complex conjugate of that current, and we get our complex power supplied by the source. So see, we did everything here by really eliminating the transformer, if you will. Again, the transformer is there, but it's like kind of using Thevenin impedance and Thevenin resistance, and using, or Thevenin model. The circuit's still the same, right? Whether we Thevenize it or not and use that to analyze the circuit's still there. We're still using the transformer is still there, but we analyze and then using this transformation from one side to the other, and it's really like an extension to the Thevenin concept. It's the same thing. All right, let's look at one more here. And on this one, it says, well, this is the same one we did before. We already did this one, right? This is the one with the ideal transformer rated at 2400, 120. So this is the same example we did before. So I don't think we have to do it again. It's right here, right? So remember, so this is the end of the chapter. So we have used magnetically coupled circuits as the basis for introducing transformers, right? So the things to remember about magnetically coupled circuits is basically how we use the dot convention, and to remember that, you know, how voltages are generated on the primary side and the secondary side due to the self-induced terms and the mutually induced terms of voltage. And then we use that to extend that idea to ideal transformers. And as you can probably see, ideal transformers are actually simpler to analyze than mutually coupled circuits. Just because an ideal transformer basically eliminates a few of the things we couldn't eliminate in mutually coupled circuits. First of all, we assume that the mutual inductance is, or the inductance is given by a perfect number, the square root of L1, L2, product of L1, L2, and the decoupling coefficient is always equal to 1. So that makes things simpler. We assume those conditions, and it makes the analysis of transformers a lot easier. Okay, so this concludes this chapter.